In the vast dark, our entire galaxy might be floating inside a hole 1 billion light-years wide, a hole with almost nothing in it. Astronomers found the gap by accident, staring at numbers that refused to make sense, and the deeper they looked, the stranger it got. You are about to travel through a bubble of missing galaxies, a void so massive it could swallow the Milky Way 1,000 times over. We will visit the scientists who first spotted the silence in their data, a void so large it hid 100 galaxies from human eyes for decades, and a number that is breaking one of the biggest theories in physics. If you love stories where the universe hides its biggest secrets in plain sight, hit subscribe, because this one goes deep. We may be living in the emptiest neighborhood in the known universe. Prepare yourselves, we begin. Somewhere in the 1980s, a small team of astronomers pointed a telescope at the sky and started counting galaxies. They expected a normal night of work. They got a mystery instead. The telescope sat on Mount Hopkins in Arizona, a peak topped with a modest reflector. Night after night, the team recorded the light from thousands of distant galaxies. They were not hunting for anything strange. They were building a map, one galaxy at a time, like marking dots on a globe. Then the numbers stopped adding up. In one direction, the galaxies vanished. Not slowly, not gradually. They dropped off a cliff, then reappeared far beyond where they should have been. It was as if someone had erased a chunk of the universe and stitched the picture back together. At first, the astronomers assumed it was a mistake. Bad equipment, a smudge on a lens, a miscount. Space does not simply run out of galaxies for hundreds of millions of miles and then start again, or so they thought. They checked their instruments. They checked their math. They pointed the telescope at the same patch of sky again, hoping for a different answer. The gap held. This was not one bad measurement. It was consistent, night after night, field after field. Something enormous and mostly empty sat in front of them, and nobody had planned to find it. Here is the picture to hold on to. Imagine standing in a crowded football stadium, and suddenly, for the space of 10,000 empty seats, there is nobody there. No usher walking by, no fan grabbing a hot dog, just silence and empty plastic seats stretching on and on. Then, past that gap, the crowd picks back up like nothing happened. That is roughly what these astronomers were staring at, except their stadium was the universe, and their empty seats were hundreds of millions of light-years of missing galaxies. The team had no name for it yet, no headline, no confirmed size, just a nagging, stubborn gap in their data that refused to explain itself. What they had actually stumbled onto was the first real evidence of a cosmic void, a region of space with dramatically less matter than everywhere else. It would take decades, better telescopes, and more teams of scientists working across different countries to figure out how big this emptiness truly was. But it started here, a handful of researchers, a modest telescope, and a silence in the numbers that would not go away. This gap did not just sit quietly in a filing cabinet. It kicked off one of the strangest ongoing investigations in modern astronomy. Because if this pocket of nothing was real, and if it was big enough, it would not just sit out there in some distant, forgotten corner of space. It might be sitting right on top of us. To understand the void, you first need to understand the tool that found it. That tool is called a redshift survey, and it works a lot like measuring how far away a siren is by how its pitch changes. Picture an ambulance racing past you on the street. As it approaches, the siren sounds higher. As it speeds away, the pitch drops lower. The sound waves are getting stretched and squeezed by motion. Light behaves the same way. When a galaxy moves away from us, its light stretches out, shifting toward the red end of the color spectrum. The faster it moves away, the more the light stretches. Astronomers call this a redshift, and it becomes a kind of cosmic speedometer. Here is the twist that makes it powerful. In our expanding universe, almost everything is moving away from everything else, and the farther away a galaxy sits, the faster it appears to recede. So, if you measure how red a galaxy's light has become, you can calculate roughly how far away it is. That is the entire engine behind a redshift survey. Astronomers point a telescope at a patch of sky, catch the light from thousands of galaxies, measure how much each one has redshifted, and use that number to plot a distance. Do this over and over, across thousands of galaxies, and something remarkable happens. You are no longer looking at a flat photograph of the night sky. You are building a three-dimensional map with real depth, showing which galaxies sit close to us and which ones sit unimaginably far. Think of it like sonar on a submarine. A ping goes out, bounces off something in the deep, and comes back with a location. Except instead of sound waves, astronomers are using stretched light, and instead of a school of fish, they are locating entire galaxies, each one containing billions of stars. In the late 1970s and through the 1980s, teams working from observatories in Arizona and Chile began running exactly this kind of survey, one galaxy at a time, one redshift at a time. It was slow, patient, unglamorous work. A single observing run might record a few thousand galaxies over months of clear nights. But patient work builds real maps. And when these early maps started coming together, they revealed something nobody had expected. Galaxies were not scattered randomly through space, like sprinkles on a cupcake. They clumped into strings and sheets, wrapping around enormous pockets of nothing. The universe was not smooth. It looked more like a sponge or a pile of soap bubbles, with galaxies clinging to the thin walls between empty pockets of space. This bubbly structure explained the strange gap the astronomers had spotted. It was not a broken instrument or a bad night of data. It was one bubble in an enormous cosmic foam, and this particular bubble happened to be enormous. Once scientists had the tool to measure it properly, they could finally start asking the real question: how far did this bubble stretch? And more importantly, where exactly were we sitting inside it? The number that first caught everyone's attention was oddly specific: 6,000 kilometers per second. That is roughly how fast the light had to shift before the galaxies started appearing again in one particular direction of the sky. Below that number, nothing. Above it, galaxies picked back up as if a curtain had lifted. 6,000 kilometers per second sounds abstract until you convert it into distance. Using the expansion rate of the universe, that gap translates into a stretch of roughly 250 million light-years, with almost no galaxies inside it. For comparison, our entire Milky Way galaxy is only about 100,000 light-years across. This gap could swallow more than 2,000 Milky Ways lined up edge to edge and still have room left over. The astronomers who first noticed this were running what is called a redshift survey of the northern sky, carefully logging galaxy after galaxy. When they wrote up their findings, they described identical gaps showing up in 3 separate regions they observed. Not one fluke measurement, 3 separate confirmations, in 3 different patches of sky. That kind of repetition is what turns a strange coincidence into real science. If the gap had shown up once, it might be dismissed as noise, like static on an old radio. But when the exact same silence appears again and again across independent observations, it stops being noise. It becomes a signal. Here is a comparison that makes the scale click. Imagine flying across the entire continental United States, coast to coast, roughly 2,500 miles. Now, imagine that gap in the galaxy data stretched about 100 times that distance. That is the kind of emptiness these astronomers were staring down. At the time, nobody used the word void with full confidence. The data was too new, the sample too small, the implications too enormous to accept right away. Science moves cautiously on purpose, because bold claims need bold evidence, and one survey from one telescope was not yet enough to declare the discovery of the emptiest region ever found near our galaxy. But the seed had been planted. A quiet region in space, confirmed independently 3 separate times, sitting almost within our own cosmic backyard. Other astronomers around the world took notice. If this gap was real, it needed to be measured properly, mapped in 3 dimensions, and checked against other independent surveys running in different countries with different telescopes. The race to understand the emptiness was just getting started, and it would eventually stretch far beyond that original patch of northern sky, revealing something even larger hiding in the darkness. Before going any further, it helps to clear up a common misunderstanding. A cosmic void is not truly empty. It is closer to a starving region of space, one that never got enough matter to build a normal share of galaxies. Picture a garden where someone scattered seeds unevenly. Some patches got clumped together, dense with seeds, and grew into a thick tangle of plants. Other patches barely got any seeds at all, and only a few scattered sprouts pushed up through the dirt. The garden as a whole still has plenty of plants, but some sections look lush and crowded, while others look sparse and lonely. The universe formed in almost exactly this way. Just after the Big Bang, matter was spread out, almost perfectly evenly, but not quite. Tiny ripples in density existed everywhere, leftover fluctuations from the earliest moments of the cosmos. Some regions started out with slightly more matter packed in. Other regions started out with slightly less. Gravity took those tiny differences and turned them into something dramatic. In the crowded regions, extra matter pulled in even more matter, snowballing over billions of years into galaxies, clusters, and enormous chains of structure. In the sparse regions, there simply was not enough material to hold on to. Whatever matter existed, there slowly drained away, pulled toward the denser neighborhoods nearby. That draining effect is the real story behind a void. It is not a hole punched into space. It is a region that lost a cosmic tug of war, watching its own material get pulled toward richer, denser areas over billions of years. Scientists measure voids by comparing their density to the average density of the universe. A typical void found in these surveys runs somewhere between 10 and 30% of the cosmic average. That means a void is not 100% empty. It still holds gas, dark matter, and occasional lonely galaxies drifting through the gap. It is simply thinner, quieter, and far less crowded than everywhere else. Here is a comparison a lot of people can picture. Think of the difference between a busy shopping mall on a Saturday afternoon and that same mall at 4 in the morning. The lights are still on. A few employees might still be walking around. But the crowd, the noise, the density of people, all of that has drained away to almost nothing. That 4 in the morning mall is what a cosmic void looks like, stretched across hundreds of millions of light years. Understanding this distinction matters because it changes the entire question these astronomers were chasing. They were not searching for a hole that broke the laws of physics. They were searching for the edges of an enormous, quiet neighborhood, one that had simply been left behind while matter piled up elsewhere. And once they accepted that voids were a real, expected feature of a universe built by gravity, the next question became impossible to ignore. If gaps like this existed throughout the cosmos, was our own galaxy safely tucked into a crowded, average neighborhood, or were we sitting inside one of the empty ones? By the mid-1980s, enough redshift surveys had piled up to reveal something nobody had fully pictured before. The universe was not spread out evenly, like sand on a beach. It was structured, almost architectural, built from repeating shapes on a scale that dwarfs anything on Earth. A team mapping galaxies in a thin strip of sky produced a chart that looked less like a scientific diagram and more like a wedge of soap bubbles. Galaxies clustered into thin, curved sheets, those sheets wrapped around gigantic pockets of empty space. Where the sheets crossed each other, dense knots of galaxies piled up, almost like intersections on a highway map. This pattern earned itself a nickname among researchers: the cosmic web. Picture a kitchen sponge held up to the light. A sponge is not solid, and it is not empty either. It is made of thin walls of material surrounding countless open pockets of air. Squeeze it, and you can feel both the structure and the emptiness working together. The universe, at its largest scale, looks remarkably similar. Galaxies gather along thin walls and stretched out filaments, the sponge's structural threads. Between those threads sit the voids, the open pockets of the sponge, holding far less matter than the walls around them. Modern surveys have measured just how much of the universe is taken up by these empty pockets. Voids make up roughly 80% of the total volume of the universe, while holding only about 20% of its mass. Nearly all of the matter that makes stars, galaxies, and planets crowds into the remaining fifth of space, packed along the sponge's thin walls. That number is worth sitting with for a moment. 4/5 of the universe, by sheer volume, is these quiet, underpopulated regions. The crowded, familiar, galaxy-filled universe most people picture is actually the minority landscape. Emptiness is the default. Crowding is the exception. Astronomers began mapping these structures with real names. Long, stretched chains of galaxies became known as filaments, like threads running through the cosmic sponge. Flattened, wall-like clusters of galaxies became known as sheets. And where multiple filaments crossed paths, dense clusters formed, known as nodes, the busiest, most crowded intersections in the entire universe. Each void sat nestled between these structures, bounded by walls of galaxies on every side, like a courtyard surrounded by buildings. This new picture completely reshaped how scientists thought about the universe's architecture. It was not a random scatter of galaxies. It was a woven structure, built slowly over billions of years by gravity, pulling matter into threads and walls, while leaving enormous pockets behind. And once researchers accepted that this sponge-like structure was the true shape of the cosmos, an unavoidable question followed close behind. Which part of the sponge do we actually live in? Are we tucked safely inside one of the crowded walls, surrounded by galactic neighbors on every side? Or are we floating inside one of the empty pockets, farther from the crowd than anyone had ever suspected? The search for our exact address in the cosmic sponge did not take scientists to some distant corner of the universe. It took them right next door. In the late 1980s, an astronomer studying nearby galaxies noticed something odd while mapping the region surrounding our own cosmic neighborhood. In one direction of the sky, galaxies simply thinned out, not far away, on the other side of the scale of the universe, practically next to us. This nearby gap became known as the local void. Unlike the earlier discoveries buried deep in redshift survey data, hundreds of millions of light-years out, the local void sat almost embarrassingly close. Its estimated size runs somewhere between 100 million and 200 million light-years across, depending on which boundary a scientist chooses to draw. Compared to the giant voids found deeper in the universe, this one is modest. But compared to anything humans build or imagine on Earth, it remains almost impossible to picture. Here is a way to feel that scale. If our entire Milky Way galaxy, 100,000 light-years across, were shrunk down to the size of a single grain of sand, the local void at that same scale would stretch across an area larger than a football field. One grain of sand, sitting near the edge of a nearly empty field. Astronomers studying this region noticed something tricky about it too. A large portion of the local void sits hidden behind the flat disk of our own galaxy. The thick band of stars, gas, and dust that makes up the Milky Way's disk blocks direct observation of a wide swath of sky. It is a bit like trying to study the layout of a neighborhood while a giant curtain blocks half your view out the window. Because of that obstruction, astronomers had to piece together the shape of the local void indirectly, studying it through the small gaps where the galactic disk did not block the view, and by tracking how nearby galaxies were moving. And moving is the key detail. Galaxies near the edge of the local void showed a telltale sign that something odd was happening nearby. They were not just drifting outward with the general expansion of the universe. Some were drifting away from the void's direction with a small extra push, as though something invisible were gently shoving them out of the emptiness. That extra push became one of the strongest pieces of evidence that this void was real. not just an illusion caused by an incomplete map, real, physical, and shaping the motion of galaxies within it. For the first time, this was not a distant curiosity hundreds of millions of light years away. It was practically knocking on our door, which raised the far more personal question. If a genuine void sat this close to our own galaxy, exactly how close were we standing to its edge? Or, more unsettling still, were we not standing near the edge at all? Were we standing somewhere closer to the middle of the emptiness? Pinpointing our exact position inside the local void required patience most people would find unbearable. Astronomers had to plot the location of thousands of nearby galaxies, one careful measurement at a time, then work backward to figure out where the emptiness actually began and ended. The center of the local void, as best researchers can calculate, sits at a specific point along the plane of our galaxy, hidden partly behind the thick band of stars that blocks a chunk of our view. Reconstructing its true center meant combining observations from multiple wavelengths of light, since visible light alone could not punch through the galactic disk's obstruction. What emerged from that painstaking process was a boundary. The local void appears to begin almost immediately outside our own small cluster of galaxies, known as the local group. In cosmic terms, this is uncomfortably close. It is not a void discovered light years away in some remote corner of the universe. It borders our own galactic neighborhood directly. Here is a comparison that helps the scale sink in. Imagine your house sits at the very edge of a massive, mostly abandoned stretch of land, the kind you might see on the outskirts of a small town, miles of open fields with no other homes in sight. Your house is not floating in the middle of that emptiness. It sits right at the border, close enough to see the empty land stretching out from your back window, but still within reach of your own small cluster of neighbors. That is roughly the position of our galaxy relative to the local void. We sit near its edge, close enough that its emptiness genuinely affects the motion of galaxies around us, but not floating dead center inside it. This edge position turned out to matter scientifically. Astronomers, studying the motion of nearby galaxies, found that many of them are drifting with unusual velocities, nudged by the uneven distribution of matter surrounding them. Our own galaxy shows hints of this same effect, caught in a gentle gravitational tug between the crowded regions nearby and the emptiness of the void just beyond our doorstep. Confirming an edge position, rather than a dead center position, took years of painstaking measurement, cross-checking data from multiple independent surveys to rule out errors caused by the galaxy's own obstruction. Slowly, the picture solidified. We are neighbors to an enormous emptiness, living right along its border. But here is where the story takes an unexpected turn. The local void, sitting so close and so personal, was not the end of the investigation. It was only the first layer, because as more surveys stacked up, covering wider patches of sky and reaching farther into the depths of space, scientists began noticing something even stranger. The local void appeared to be just one small piece nested inside something far, far larger. Something that would not just border our galaxy, something that might contain it entirely. Before diving into whatever larger structure surrounds us, it helps to understand exactly what us means on a cosmic scale. Our galaxy does not float through space alone. It belongs to a small cluster of galaxies known as the local group. Picture a neighborhood with roughly 100 houses, but only 2 mansions dominate the skyline, while the rest are modest cottages scattered around them. The local group works the same way. It contains around 100 known galaxies, but only 2 truly massive ones tower over the rest: our own Milky Way and its larger neighbor, the Andromeda Galaxy. Every other galaxy in the group is a smaller companion, orbiting in the gravitational shadow of these 2 giants. The entire local group stretches across roughly 10 million light-years. That sounds enormous, and by human standards it is beyond comprehension. But compared to the void sitting just beyond its borders, the local group is genuinely tiny, a small gathering of houses at the edge of a vast, empty countryside. This matters because it changes how we should picture our galaxy's situation. The The Milky Way is not floating alone at the edge of the local void. It is huddled together with its neighbors, this modest cluster of roughly 100 galaxies, all clinging close to one another near the boundary of the emptiness. Here is a helpful comparison. Think of a small cluster of streetlights glowing at the very edge of a dark, unlit field stretching for miles. The streetlights, representing our local group, cluster together for mutual support, their light overlapping and reinforcing each other. Just beyond them, the darkness of the empty field takes over completely. Scientists studying the motion of the local group found something revealing. The entire cluster, Milky Way, Andromeda, and every smaller galaxy in between appears to be drifting through space at a specific velocity, and part of that drift lines up with the pull of denser regions nearby, along with a gentle push from the emptiness of the void behind us. That detail turns the local group from a static cluster into something more like a small boat caught in a current, being pulled toward crowded harbors on one side while being nudged away from open water on the other. Understanding this small cluster of galaxies as its own tightly bound unit set the stage for the next major discovery, because the local group itself, as it turns out, is not simply floating in isolated space near one modest void. It belongs to something dramatically bigger, a structure so large it would eventually force astronomers to reconsider not just our galaxy's neighborhood, but our entire cosmic address. In 2013, 3 astronomers published a discovery that would eclipse everything found before it. Their names were Ryan Keenan, Amy Barger, and Lennox Cowie, and the underdense region they identified would come to carry their initials, the KBC void. Some scientists preferred a blunter name. They called it the local hole. This was not the modest, nearby local void from earlier. This was something on a completely different scale. The underdensity is proposed to be roughly spherical, approximately 2 billion light-years in diameter. 2 billion, not 200 million, 10 times larger than the void bordering our own galaxy. Here is a way to feel that jump in scale. If the earlier local void was like an empty field on the edge of town, the KBC void is like an empty region the size of an entire continent, one so large that entire countries' worth of galaxies simply never formed inside it. And the detail that stopped astronomers in their tracks was not just the size, it was the location. The underdensity contains the Milky Way, the local group, and the larger part of the Laniakea supercluster. Our galaxy was not near the edge of this one. Our galaxy was inside it. The Milky Way sits within a few 100 million light-years of the void's center, not at the border, not clinging to the edge like we do with the smaller local void. Genuinely, deeply inside this enormous, underdense region, closer to its heart than to its walls. Keenan, Barger, and Cowie had not stumbled onto a small local curiosity. They had potentially found the address of our entire galactic neighborhood, and the address read, floating inside one of the emptiest known regions in the observable universe. Naturally, a claim this dramatic needed serious scrutiny. A void 2 billion light-years wide, with our galaxy sitting near its center, is the kind of finding that reshapes textbooks if it holds up. Extraordinary claims require extraordinary evidence, and one team's analysis, however careful, was not going to settle the question alone. Other researchers began digging through independent datasets, checking galaxy counts across different wavelengths, cross-referencing supernova positions, and testing whether this underdensity showed up consistently, no matter which method was used to measure it. The debate that followed would stretch on for years, pulling in cosmologists from multiple countries, multiple institutions, and multiple, sometimes conflicting theories about how the universe is supposed to be built. Because if the KBC void was real, it would not just rewrite our galaxy's cosmic address. It might help explain one of the most stubborn, unresolved mysteries in modern physics, a number that refuses to agree with itself, no matter how carefully scientists measure it. Numbers like 2 billion light-years slide past most people without leaving a mark. The scale is too large for human intuition to grasp on its own, so it helps to break it down piece by piece, building the picture from something familiar, Start small. Light travels at roughly 6 trillion miles every year. That single year of travel, 6 trillion miles, is called a light year. Already, this number strains the imagination, since nothing on Earth moves anywhere close to that speed. Now stack that distance. Our entire Milky Way galaxy, home to over 100 billion stars, stretches across roughly 100,000 light years. That means light itself, the fastest thing in existence, takes 100,000 years just to cross from one side of our galaxy to the other. The KBC void spans 2 billion light years. To cross from one Milky Way galaxy width to a void that size, you would need to line up 20,000 Milky Ways, edge to edge, in a single row. Here is a comparison that might land better. Imagine every grain of sand on every beach on planet Earth. Scientists estimate that number lands somewhere in the range of several quintillion grains. Now imagine trying to count them one at a time, at a rate of 1 grain per second, without ever stopping to sleep, eat, or rest. You would still be counting long after every human alive today had died, and long after their descendants had died too. That is the kind of scale gap between something a human mind can casually picture and the true size of this void. Or try a simpler visual. Picture the entire United States, coast to coast, roughly 2,500 miles. The KBC void, converted into a single straight line, would be so long that this same coast-to-coast American road trip would need to happen more than 400 trillion times in a row before you covered the same distance. Numbers this large stop being about counting and start being about a feeling of profound, almost dizzying emptiness. 2 billion light years of space, and inside a huge portion of it, matter simply never gathered the way it did everywhere else. And somewhere near the center of that emptiness, according to the astronomers who first mapped it, sits our own galaxy, our sun, our planet. Every person who has ever lived, sitting inside a void that dwarfs almost anything the human mind is built to comprehend. Grasping that scale is the first step toward understanding why this discovery mattered so much to scientists. Because a void this size does not just represent an interesting quirk of galaxy counting, it threatens to rewrite the rules that describe how the entire universe is supposed to be built. Every major scientific discovery has a human story behind it, and the KBC void is no exception. Behind the 2 billion light-year measurement stood a small team of researchers, piecing together clues from galaxy surveys that had been slowly accumulating for decades. Ryan Keenan, Amy Barger, and Lennox Cowie studied the underdensity in 2013, combining their initials into the name that stuck. Their work did not come from a single, flashy observation. It came from painstakingly comparing galaxy counts across multiple regions of sky, checking whether the underdensity held up consistently, no matter which direction they looked. This kind of research rarely makes headlines while it is happening. It looks, from the outside, like tedious data work, counting galaxies, cross-referencing distances, running statistical checks to rule out errors. But this quiet, careful process is exactly how real discoveries get confirmed, brick by brick, rather than through a single dramatic moment. Our own Milky Way galaxy lies in a void called the KBC void, or local hole, and confirming that fact meant the team had to rule out every boring explanation first. Could it be dust blocking their view? Could it be an error in how distances were calculated? Could it be a fluke limited to one particular survey? One by one, those explanations fell away, leaving behind a genuine, physical underdensity in the distribution of galaxies surrounding our own cosmic neighborhood. Here is a comparison that captures what this kind of research actually feels like. Imagine you suspect your neighborhood has fewer streetlights than every other neighborhood in your city. You could just say it looks dim and move on. Or you could walk every single block, count every single streetlight, compare your counts to 5 other neighborhoods, and rule out the possibility that it was simply a cloudy night that made things look darker than they really were. That second approach, slow, methodical, and thorough is what separates a hunch from a scientific discovery. It is exactly what Keenan, Barger, and Cowie did, except their neighborhood stretched across 2 billion light-years, and their streetlights were entire galaxies. Their published findings did not claim absolute certainty. Science rarely deals in absolute certainty. Instead, their work presented strong statistical evidence, the kind other scientists could test, challenge, and build upon. And test it. Other scientists did. Almost immediately after publication, researchers around the world began running their own independent checks, using different telescopes, different wavelengths of light, and different mathematical models. Some of those checks would strengthen the case for the void's existence. Others would raise uncomfortable questions about whether a void this size could even exist under the current scientific understanding of how the universe formed. That tension between confirming evidence and troubling theoretical questions is exactly where the story gets more interesting. Because a discovery this big does not just sit quietly in a journal. It forces physicists to ask whether something is wrong, not with the void, but with the very theory used to describe the entire universe. Numbers alone rarely tell the full story, so it helps to translate the KBC void's emptiness into something a person can actually picture pressing against their own skin. This underdensity features a matter density about 20 to 30% lower than typical regions of the universe. On paper, that might sound almost modest. 20 to 30% hardly sounds catastrophic, the kind of number you might see on a discount sticker at a grocery store. But scale that percentage up to the size of an entire cosmic region spanning billions of light years, and the missing matter adds up to an almost incomprehensible quantity. Entire generations of galaxies that simply never formed. Here is a comparison that brings the number down to earth. Picture a full stadium built to hold 100,000 fans. Now, imagine that same stadium missing 25,000 of those fans, not scattered randomly throughout the seats, but concentrated in one enormous shape that fans could plainly see if they looked around. The stadium would still function, games would still happen, but anyone paying attention would immediately notice something felt wrong, quieter, thinner, missing a real chunk of its expected crowd. That missing quarter of the crowd is roughly the scale of what this void represents, stretched across billions of light years instead of stadium seats. This missing matter matters scientifically because gravity depends directly on how much mass exists in a given region. Less matter means less gravitational pull holding that region together, and less gravitational pull changes how space itself behaves inside the void, compared to the denser regions surrounding it. Voids are regions of the universe where the density is below average, and supervoids are voids larger than about 300 million light-years. According to cosmologist Indranil Banik, one of the researchers who has spent years studying exactly this effect, the KBC void, at 2 billion light-years across, sits firmly in supervoid territory, one of the largest examples scientists have ever proposed. Living inside a region with 20 to 30% less gravitational pull than average carries consequences beyond just having fewer galactic neighbors. It can subtly affect how far space itself appears to stretch in our local cosmic neighborhood compared to regions farther away, packed with their expected quota of matter. That subtle effect turns out to connect directly to one of the strangest unsolved puzzles in modern cosmology, a persistent disagreement between two completely different methods of measuring how fast the universe expands. But before diving into that mystery, there is one more piece of context worth understanding. Because our galaxy is not just floating somewhere generically inside this void, we belong to a specific, named structure inside it, one that carries its own dramatic story about just how enormous our true cosmic neighborhood really is. Every home has an address, and galaxies are no exception. Ours happens to belong to a structure with one of the most beautiful names in modern astronomy, Laniakea, a Hawaiian word meaning immense heaven. The Laniakea supercluster represents the next tier up from our small local group of roughly 100 galaxies. Where the local group is a modest neighborhood, Laniakea is closer to an entire metropolitan region. a sprawling supercluster containing roughly 100,000 galaxies bound together by gravity across a truly staggering distance. That distance stretches approximately 500 million light-years across, according to researchers who mapped its boundaries by tracking the motion of thousands of galaxies, watching which direction they flowed under gravity's pull. Just as water flows downhill toward a river basin, galaxies flow gravitationally toward the densest regions of their supercluster. Here is a comparison worth sitting with. If our local group of 100 galaxies is like a small town, Laniakea is like an entire country, containing thousands of towns just like ours, all connected by invisible gravitational roads that determine which direction everything eventually drifts. And remarkably, the KBC void contains the larger part of this entire supercluster, not just our small local group, not just our galaxy. The majority of this massive, 500 million light-year wide structure sits inside the boundaries of the enormous underdense region first mapped by Keenan, Barger, and Cowie. This detail reshapes the entire scale of the discovery. It is not simply that our galaxy happens to sit inside a void. An entire supercluster, containing roughly 100,000 galaxies, calls this underdense region home. Picture an entire country built inside a vast, sparsely populated stretch of land. A country that still manages to build cities and towns despite the surrounding emptiness pressing in from every direction. That is essentially what Laniakea represents, a genuine, populated supercluster existing inside one of the emptiest known regions of the observable universe. This raises an important clarification worth remembering. A void being underdense does not mean it contains zero galaxies. It means the region holds dramatically fewer galaxies than an average patch of the universe its same size would typically contain. Laniakea proves that point perfectly. An entire supercluster thriving inside a region still classified as a supervoid. Understanding our address this way changes the entire emotional weight of the discovery. We are not isolated specks floating alone in cosmic nothingness. We are residents of a genuine, populated supercluster, one that happens to sit inside a much larger stretch of underdense space. But that population inside the void is not evenly distributed either. Galaxies inside underdense regions tend to cluster together and get pushed towards specific locations, almost like crumbs shaken to the edges of a bowl. And understanding exactly why that happens reveals one of the most important physical processes shaping the entire structure of the void itself. Voids are not static. They behave more like a slow, billion-year-long shaking motion, constantly redistributing whatever matter sits inside them. Picture a bowl of mixed nuts, the kind with peanuts, cashews, and larger almonds all jumbled together. Give that bowl a good shake, and something predictable happens. The smaller peanuts sink toward the bottom, while the larger, bulkier pieces work their way up toward the surface and drift toward the edges of the bowl. Cosmic voids perform a similar sorting process, except the shaking force is gravity, and the timescale stretches across billions of years instead of a few seconds. Here is how it actually works. Inside a void, matter is thin and gravity is weak, but at the void's boundary, dense walls and filaments of galaxies exert a much stronger gravitational pull. Over enormous stretches of time, whatever matter exists inside the void slowly drifts outward, pulled toward those denser walls, like loose crumbs sliding toward the rim of a shaken bowl. As voids expand, they push galaxies and dark matter toward the boundaries, creating the filamentary structures that define the cosmic web. This is not a one-time event. It is an ongoing, active process, still happening today, still reshaping the void's contents even as astronomers study it. The reason this happens connects directly to how gravity and expansion compete with each other. The lack of mass in a void means there is less gravity to counteract cosmic expansion, so voids grow over time, pushing matter outward into surrounding walls and filaments. Weak gravity loses the tug-of-war against the universe's constant outward stretch, and whatever material remains slowly empties out toward the crowded boundaries. Here is a comparison that might make the physics click. Imagine standing in the middle of an emptying parking lot after a concert ends. At first, cars are scattered everywhere, but slowly, one by one, they funnel toward the exits, the crowded, high traffic boundaries of the lot. The center of the lot empties out faster and faster, not because anyone forced it, but simply because every path eventually leads toward the exit. This slow drainage process explains why voids do not stay static once they form. They actively grow emptier over time, while their surrounding walls grow correspondingly denser, reinforcing the entire bubble and thread structure of the cosmic web. It also explains something crucial about our own position. If galaxies naturally drift from the void center toward its edges over billions of years, then the exact location of our galaxy inside the KBC void, whether closer to its heart or closer to its boundary, carries real physical meaning about how this ancient sorting process has played out over cosmic time. And that sorting process does something else, too. It speeds up the void's growth in a way that ripples outward, eventually influencing something as fundamental as how fast space itself appears to expand. Which brings the story to one of the strangest physical properties belonging to any void. Here is a detail that surprises most people the first time they hear it. Empty regions of the universe do not just sit passively, waiting to be filled. They actively expand faster than crowded regions do. This sounds backward at first. Emptiness feels like it should mean nothing is happening, but the physics tells a different story entirely. Voids expand faster than the rest of the universe because they are underdense. The explanation connects back to that same tug-of-war between gravity and cosmic expansion introduced earlier. Gravity constantly works to slow down or resist the universe's overall stretch. But gravity needs matter to do its job, and voids, by definition, are running short on matter. The void density measures 10 to 30% of the cosmic average, and voids expand faster than the cosmic average, contributing to the apparent acceleration of the universe's growth in these regions specifically. Here is a way to picture this. Imagine 2 rooms filled with balloons, each room slowly being pumped full of extra air, causing the walls themselves to stretch outward. One room is packed wall to wall with heavy furniture, weighing down the floor and resisting the stretch. The other room sits nearly empty, nothing weighing it down, nothing resisting the expansion at all. The empty room's walls stretch outward more freely and more quickly, simply because nothing inside is holding them back. That difference in resistance is essentially what happens with gravity across the universe. Dense regions, packed with galaxies and matter, generate enough gravitational pull to noticeably slow down their local expansion. Underdense voids, lacking that gravitational anchor, expand with comparatively little resistance. This creates a strange, almost paradoxical effect. The very emptiness of a void causes it to grow emptier still, faster than the crowded regions around it, which reinforces the entire structure of the cosmic web over time. Voids widen, walls thicken. The contrast between crowded and empty regions grows more extreme the longer the universe continues expanding. This faster expansion inside voids is not just an interesting side detail. It carries a much bigger consequence for anyone living inside one, which includes us. If our own galaxy sits within an underdense region, like the KBC void, then the local rate of cosmic expansion we measure from Earth could be subtly, systematically different from the true, universal average. That single idea, a possible local boost to our measured expansion rate, connects directly to one of the most stubborn, unresolved arguments in all of modern physics, a number that different scientific methods simply refuse to agree on, no matter how carefully each one gets measured. But before untangling that mystery, it helps to see just how extreme cosmic emptiness can get elsewhere in the universe. Because the KBC void, as enormous as it is not actually the largest void ever discovered. Long before astronomers found the KBC void surrounding our own galaxy, they stumbled onto an even stranger example of cosmic emptiness. One so extreme, It earned a nickname straight out of a horror movie, the Great Nothing. The Boötes void is a spherical area in the constellation Boötes, spanning an area 330 million light-years across, but containing very few galaxies, making it the largest such void in the known universe. To understand how strange this discovery felt, consider the math. This huge expanse contains just 60 or so galaxies, all in a tube-shaped region that lies across the middle of the void. Scientists would normally expect there to be around 2,000 galaxies in an area of the same size. 60 galaxies, where 2,000 should exist. That is not a modest shortage. That is a 97% vacancy rate, an emptiness so severe it almost defies explanation. Here is a comparison that captures the shock value. Imagine a massive sports arena built to comfortably seat 2,000 fans, one of the largest venues in the country. Now imagine walking inside on game night and finding only 60 people scattered across the entire building, most of the seats stretching out empty in every direction, echoing footsteps, the only sound bouncing off the walls. That eerie, echoing emptiness is exactly the kind of scene astronomers were confronting when they first mapped the Boötes void. One astronomer's comment about the discovery captured the strangeness perfectly. Astronomer Greg Aldering noted that if the Milky Way had been in the center of the Boötes void, humanity would not have known there were other galaxies until the 1960s. Think about that for a moment. An entire civilization staring up at what looked like an empty, starless void, having no idea that trillions of other galaxies existed just beyond their limited view, simply because the emptiness surrounding them stretched too far for early telescopes to see past. The Boötes void remains larger than the KBC void that surrounds our own galaxy, but its extreme emptiness, that 97% missing galaxy count, makes it the most dramatic example scientists have found of just how thin these cosmic gaps can become. Its discovery mattered for another reason too. It proved that voids this size, this severely underdense, were physically possible somewhere in the universe, which meant the KBC void surrounding our own galaxy was not some implausible, one-off anomaly. It fit into an established pattern, a universe genuinely capable of building enormous, echoing pockets of nothing, scattered throughout the cosmic web. And if voids this extreme exist elsewhere, the next uncomfortable question becomes impossible to avoid. What would it actually feel like, day to day, to live inside one of these enormous gaps without ever realizing the emptiness surrounding your own cosmic neighborhood? Here is the unsettling part of this entire story. If our galaxy genuinely sits inside the KBC void, nothing about our daily experience would tip us off. No alarm goes off. No visible warning sign appears in the night sky. The stars overhead still shine. The moon still orbits. The sun still rises every morning exactly as it always has. Living inside one of the emptiest known regions of the observable universe produces zero noticeable symptoms for anyone standing on the surface of a planet. Looking up, that is precisely what makes voids so difficult to detect in the first place. Greg Aldering's comment about the Boötes void applies just as easily to our own situation. A civilization living deep inside a void would have no local clue that anything unusual surrounded them, because their own tiny galactic neighborhood would still look completely normal from the inside. Here is a comparison that captures this feeling. Imagine living your entire life in a small town, surrounded by a modest scattering of houses, a school, a grocery store, everything that feels like a normal, complete little world. You have no reason to suspect anything is missing, because your daily life gives you no direct evidence of what exists or does not exist beyond the edge of town. Only by traveling far outside your familiar boundaries, or by receiving detailed maps from someone who has, would you ever discover that your town actually sits in the middle of hundreds of miles of empty countryside, isolated from any other town in every direction. That is essentially the situation our own galaxy may be in. Nothing about the Milky Way's internal experience, its stars, its planets, its billions of years of quiet stellar evolution, offers a single hint about its surrounding cosmic emptiness. The only way to detect the void at all is by looking outward, across enormous distances, and counting how many galactic neighbors do, or do not, appear. This detection challenge explains why it took until the 20th century for astronomers to even suspect something like the KBC void existed, and why confirming it required decades of increasingly precise redshift surveys, stretching across multiple independent research teams and multiple countries. It also reframes something deeply personal about this entire investigation. Every person who has ever lived, every recorded moment of human history, unfolded inside a region of space that may be dramatically emptier than the cosmic average, and not one of those billions of people ever noticed, because there was nothing to notice from the inside. The emptiness only reveals itself through careful, patient measurement, stretching telescopes toward the faint light of distant galaxies, counting what should be there against what actually is. And once astronomers accepted that this kind of invisible emptiness was truly possible, the investigation expanded further outward, uncovering yet another nearby void, sitting just beyond the boundaries already mapped, adding one more piece to an increasingly strange picture of our galaxy's true cosmic neighborhood. Just when astronomers thought they had mapped the emptiness surrounding our galaxy, another gap turned up nearby, sitting in a completely different direction of the sky. This one carries the name Southern Local Supervoid. Its center sits 96 megaparsecs away, and the void stretches 112 megaparsecs across at its narrowest width. Converting those numbers into more familiar terms, that puts its center roughly 300 million light-years from us, with the void itself stretching over 350 million light-years across. Its volume comes out to approximately 600 billion times the volume of the Milky Way galaxy. Sit with that number for a second. 600 billion Milky Ways could fit inside this single empty pocket of space. And that pocket sits right next to our own cosmic neighborhood, not buried somewhere on the far side of the observable universe. Here is a comparison that helps this land. Picture the largest lake you have ever seen. Something like one of the Great Lakes stretching to the horizon in every direction. Now, imagine discovering, almost by accident, that there is a second enormous lake sitting just beyond the hills you always assumed were solid land, a lake nobody had properly mapped before because it sat in an inconvenient direction, hard to survey completely. That is roughly what happened here. The Southern Local Supervoid sits adjacent to the local supercluster, the larger structure containing our own galaxy, meaning we are not just bordered by one empty region. We appear to be surrounded by multiple underdense pockets, stacked in different directions, like empty lots surrounding a single crowded block. This discovery mattered because it reinforced a growing suspicion among cosmologists. Our galaxy's position was not a rare, isolated coincidence, one lonely void discovered purely by chance. It was starting to look like a genuine pattern, multiple confirmed underdense regions clustering around our specific corner of the universe. Finding one supervoid nearby could be dismissed as an unusual fluke. Finding a second, independently confirmed supervoid, using entirely separate survey data, made that explanation far harder to accept. Scientists studying both voids together began asking a more fundamental question. Were these separate, unrelated pockets of emptiness that happened to form near each other by chance? Or did they represent connected pieces of one much larger, more complex, underdense structure, stretching across our local region of the universe in ways nobody had fully mapped yet? Answering that question required going back to the very beginning, not the beginning of the discovery, but the beginning of the universe itself, tracing these voids back to their true origin, billions of years before any galaxy, any void, or any astronomer existed to measure them. To understand why voids exist at all, the story has to rewind to the first fraction of a second after the Big Bang, a period so early that the universe had not yet cooled enough to form a single atom. During this earliest moment, the universe underwent an event called inflation, an incredibly rapid stretching of space itself. In a fraction of a second, tiny quantum fluctuations, random ripples smaller than an atom, got stretched out to enormous cosmic scales, becoming the blueprint for every structure that would eventually form. After the Big Bang, the universe was nearly uniform but contained tiny fluctuations in density. Quantum ripples stretched to cosmic scales by inflation. These fluctuations were incredibly small, differences in density measured in fractions of a percent. But small differences, given billions of years and the patient hand of gravity, can grow into something enormous. Here is a comparison that makes this click. Picture flipping a coin 10,000 times in a row. Pure chance alone will produce small streaks, moments where heads comes up 5 or 6 times in a row before flipping back to tails. Those streaks are not meaningful on their own. But imagine some strange rule where every streak of heads made the next coin flip slightly more likely to land on heads too. Over 10,000 flips, those tiny early streaks would snowball into massive, lopsided imbalances, some stretches becoming almost entirely heads, others almost entirely tails. That snowballing effect is essentially what gravity did with the universe's original density ripples. Over billions of years, gravity amplified these fluctuations, pulling matter together in some regions while leaving others increasingly empty. Where density was slightly higher, matter began collapsing under gravity to form galaxies, clusters, and filaments. Meanwhile, regions that started with slightly lower density became emptier as matter flowed away toward denser areas. This means every void in the universe, the local void, the KBC void, the Botis void, the southern local supervoid, all trace their origin back to the exact same source. A few unlucky patches of space that started out with slightly less matter than average, back when the universe was younger than a single second old. These underdense regions evolved into cosmic voids, and in cosmological simulations, voids emerge naturally from this process, starting small in the early universe and merging over time into larger structures, much like bubbles in boiling water. That bubbling comparison captures something important. Voids did not appear instantly, fully formed. They started as modest, unremarkable dips in density, then slowly merged and grew over billions of years, exactly like small bubbles rising through boiling water, gradually combining into larger ones. Understanding this origin story changes how the entire discovery feels. The KBC void surrounding our galaxy is not some strange, isolated accident. It is the natural, expected outcome of physical laws that have been playing out since the first fraction of a second after the universe began. But knowing where voids come from raises a harder question. If this process happens everywhere, uniformly, according to well-understood physics, then why does a void as enormous as the KBC void create such intense controversy among scientists? The answer connects to the very structure holding these voids in place, the invisible skeleton of the universe itself. Every void needs boundaries, and those boundaries are built from 3 distinct types of structure, each with its own name, its own shape, and its own role in the cosmic web. The first are filaments, long, thread-like strands of galaxies stretching across space. Cosmic filaments consist of elongated, thread-like structures connecting walls and nodes, with a typical diameter of 2 to 5 megaparsecs and a typical length of 50 to 100 megaparsecs. Converting those numbers, filaments run roughly 6 to 15 million light-years thick, but stretch out 150 to 300 million light-years long, like enormous cosmic highways connecting distant regions of dense matter. Their density runs 5 to 20 times the cosmic average, and they contain galaxies arranged in linear patterns, with matter streaming along their length toward denser nodes. The second structure type is walls, flattened sheets of galaxies forming the boundaries between voids. Physical sheets are flattened, overdense structures with a typical thickness of 5 to 10 megaparsecs, spanning around 100 megaparsecs across, with a density 1 to 5 times the cosmic average. Here is a comparison for both filaments and walls together. Picture a chain-link fence stretched across an empty field. The metal wires represent filaments, thin, connecting strands running in specific directions. The flatter sections, where multiple wires overlap and cross, represent walls, denser patches formed where several strands come together into a single surface. The third structure type sits at the busiest intersections. Cosmic nodes are dense concentrations at filament intersections, typically 2 to 5 megaparsecs in diameter, with density 50 to 500 times the cosmic average. They host massive galaxy clusters containing thousands of galaxies. If filaments are highways and walls are flattened sheets, nodes are the major cities sitting at the busiest highway interchanges, packed with far more activity than anywhere else in the entire structure. Together, these three components, filaments, walls, and nodes, form the entire skeleton of the cosmic web, the scaffolding that surrounds and defines every void. Voids are not separate, isolated bubbles floating independently through space. They are the negative space carved out by this skeleton, the empty rooms bounded by walls, connected by hallways, anchored by busy intersections. This skeleton matters enormously for the ongoing scientific debate around the KBC void, because the size and shape of this skeleton, how thick the walls are, how far apart the nodes sit, how long the filaments stretch, all of it depends on the standard theory describing how the universe formed and evolved. If the KBC void turns out to be far larger than this skeleton should typically allow, based on decades of careful modeling and simulation, that discrepancy becomes a serious problem, not just an interesting curiosity, but a genuine challenge to the physics underlying the entire structure. And that challenge becomes even sharper once you realize just how much of the universe these empty rooms actually occupy, compared to the narrow hallways and busy cities that surround them. Here is a number that reframes everything discussed so far. Vast, underdense void regions occupy around 80% of the universe's volume, but contain only around 20% of its mass. Flip that statement around, and it becomes even more striking. The crowded, familiar, galaxy-filled universe, the version most people picture when they imagine the cosmos, only occupies about 1/5 of all available space. The remaining 4/5, by sheer volume, is emptiness. Here is a comparison to make this feel real. Picture a massive house with 20 rooms. Now, imagine that 16 of those 20 rooms sit completely unfurnished, empty of people, empty of furniture, just open space with the lights left on. Only 4 rooms actually contain the furniture, the people, and the activity most visitors would associate with a lived-in home. Walking through that house, most visitors would probably describe it as a home, full of life and activity, simply because the 4 furnished rooms happen to be the ones getting all the attention. But by pure square footage, that house is overwhelmingly empty. That is essentially the true shape of our universe. Galaxies, stars, and planets. Everything that makes up the version of the cosmos most people picture crowd into a relatively narrow slice of total cosmic volume. The overwhelming majority of space, by raw measurement, belongs to the quiet, sparse voids. This 80% figure did not come from a single lucky measurement. It emerged from combining data across dozens of independent redshift surveys, tracking millions of galaxies across enormous stretches of sky, then calculating exactly how much of that mapped volume fell inside confirmed underdense regions versus how much fell inside the denser walls, filaments, and nodes. Despite their emptiness, voids occupy about 80% of the universe's volume, while containing only 10% of its mass, making them critical laboratories for testing cosmological models. That last phrase matters. Voids are not just a footnote in the story of the universe's structure. They have become one of the most valuable tools scientists have for testing whether our fundamental theories about the cosmos actually hold up. Because voids are so empty, they are far less affected by the messy, complicated gravitational interactions happening inside crowded galaxy clusters. That relative simplicity makes them cleaner, easier to model mathematically, and easier to compare directly against theoretical predictions. In other words, studying the empty rooms turns out to be one of the best ways to test whether the entire house was built correctly. But not every room stays completely empty. Even inside the quietest, most underdense voids, a scattering of lonely galaxies, still manages to survive. And the story of exactly how they live inside such extreme isolation reveals something unexpected about galaxy formation itself. Even inside the emptiest regions of the universe, a small population of galaxies manages to survive, scattered thin and far apart. Scientists call them void galaxies, and studying them has revealed something genuinely surprising about how isolation shapes a galaxy's entire life. Galaxies in voids are bluer, have higher specific star formation rates, and are of later types than galaxies living in regions at average density. Breaking that down, bluer light in astronomy usually signals youth. Young, hot, newly formed stars burn with a bluer color, while older, cooler stars trend toward yellow and red. A galaxy glowing noticeably bluer than its crowded counterparts is a galaxy still actively forming plenty of fresh, young stars, rather than one dominated by older, settled stellar populations. Higher star formation rates reinforce that same picture. Void galaxies are not quiet, dying relics drifting through emptiness. They are still actively building new stars, seemingly undisturbed by the extreme isolation surrounding them. Here is a comparison that helps explain why. Picture two students growing up in very different environments. One grows up in a massive, crowded city, constantly bumping into neighbors, dealing with traffic, noise, and competition for space. The other grows up on a quiet, isolated ranch, miles from the nearest neighbor, with plenty of room to grow at their own pace, undisturbed by outside interference. Galaxies experience something similar. In crowded regions, close encounters and collisions between neighboring galaxies can strip away gas, trigger violent bursts of activity, or merge two galaxies together entirely, disrupting their natural development. Void galaxies, isolated from that crowded chaos, get left alone. Their gas supply stays undisturbed, fueling a slower, steadier, more continuous pattern of star formation. Cosmic voids account for more than half of the entire volume of the universe, with sizes lying between 1 and 100 megaparsecs, and within that enormous empty volume, void galaxies represent a kind of natural laboratory. Scientists studying them get a rare chance to observe galaxy evolution shaped almost entirely by nature alone, without the complicating influence of crowded neighbors constantly interfering. Studies have found supporting evidence for this local inhomogeneity extending down to the individual galaxy level, confirming that the physical environment surrounding a galaxy genuinely shapes its development over billions of years. This detail carries a quiet irony worth appreciating. If our own galaxy sits inside the KBC void, as the evidence increasingly suggests, we technically qualify, at least loosely, as residents of this same isolated, undisturbed cosmic environment that produces bluer, younger, more actively star-forming galaxies elsewhere in the universe. Whether that isolation has meaningfully shaped our own galaxy's history remains an open, actively studied question. But the pattern found in other void galaxies raises a tantalizing possibility that our galaxy's own relatively quiet, undisturbed history might trace back to the same underlying cause. And that same underlying emptiness connects directly to the biggest, most contentious mystery this entire investigation has been building toward. Every scientific field eventually runs into a number that simply will not behave. In cosmology, that number is called the Hubble constant, and it measures exactly one thing: how fast the universe is expanding. For decades, scientists have used two completely different methods to measure this number, expecting both approaches to land on roughly the same answer. Instead, they consistently disagree, and the size of that disagreement has only grown more stubborn the more precisely scientists measure it. Measurements of the nearby universe, using supernovae and Cepheid variables, suggest a higher value of 73 kilometers per second per megaparsec than those derived from the early universe via the cosmic microwave background and baryon acoustic oscillations, which suggests 67 kilometers per second per megaparsec. Those units sound technical, but the core idea is simple. Both numbers describe how quickly a galaxy, sitting one specific distance away, appears to be racing away from us, due to the universe's overall expansion. One method, measuring nearby stars and exploding stars called supernovae, consistently produces a faster number. The other method, analyzing the faint afterglow left over from the Big Bang itself, consistently produces a slower number. Here is a comparison that captures the frustration this causes scientists. Imagine two incredibly precise clocks, both built by expert engineers, both checked and rechecked for accuracy. Yet no matter how many times you compare them, one clock consistently runs a few seconds faster than the other every single hour. Individually, both clocks seem perfectly reliable. Together, they refuse to agree. This disagreement is called the Hubble tension, and it has become one of the most stubborn, actively debated problems in modern physics. Both measurement methods have been checked, rechecked, refined, and cross-validated by multiple independent research teams around the world. The gap between them has not closed. If anything, more precise measurements have only made the disagreement clearer. Our best theory of cosmology is wrong, according to researcher Indranil Banik, who has warned that nature does not care about our theories, no matter how elegant they might seem on paper. That kind of statement, coming from a working cosmologist, signals just how seriously the scientific community treats this unresolved gap. It is not a minor rounding error waiting to be cleaned up. It represents a genuine crack in our understanding of how the universe expands. And this is exactly where the story of the KBC void re-enters the picture, because one of the leading explanations for the Hubble tension does not require inventing entirely new physics. It simply requires accepting that we might be living somewhere unusual, somewhere emptier than average, somewhere like the inside of an enormous cosmic void. Here is where every earlier piece of this investigation finally connects into a single, unified idea. What if the entire Hubble tension is not a sign of broken physics at all, but simply a side effect of our own unusual cosmic address? If we live in a large void, the reduced gravitational pull from surrounding matter allows nearby galaxies to recede faster than expected in an average region. This local boost in apparent expansion mimics a higher Hubble constant without requiring revisions to fundamental physics or cosmology. Remember the earlier explanation about voids expanding faster than crowded regions, thanks to their weaker gravitational pull. That same effect, applied specifically to our own galaxy's position inside the KBC void, could explain exactly why local measurements of the universe's expansion rate consistently come out faster than measurements based on the ancient, early universe. Here is a comparison that makes this idea click. Imagine measuring the speed of traffic on two different sections of the same highway. One section runs through a congested downtown area packed with stoplights, pedestrians, and heavy traffic, naturally slowing everyone down. Another section runs through open, empty countryside with no obstacles slowing anyone down at all. If you only measured speed on the open countryside section, you might conclude the entire highway runs faster than it actually does on average, simply because your measurement happened to come from the least congested stretch. That is essentially the proposed explanation for the Hubble tension. Measurements based on nearby supernovae and stars are being taken from inside a genuinely underdense region, our local void. Those measurements pick up a real, local speed boost caused by weaker surrounding gravity, a boost that does not exist in the same way when measuring the universe's expansion using the ancient cosmic microwave background, which represents a much larger, more universal average. This supervoid presents a real challenge, because according to the standard model of cosmology, matter is more or less evenly distributed throughout the universe, which means a void this size, sitting in exactly the right position to explain the Hubble tension, would require rethinking that fundamental assumption of even distribution. The Hubble tension is largely a local phenomenon, with little evidence that the expansion rate disagrees with expectations further back in time. According to researcher Indranil Banik, who noted that a local solution, like a local void, is a promising way to solve the problem. This explanation carries a kind of elegant simplicity that scientists find appealing. It does not require inventing new particles, new forces, or entirely new laws of physics. It only requires accepting that our own galaxy happens to sit in an unusual, underdense neighborhood, and that this local geography subtly distorts our nearby measurements compared to the true cosmic average. But an elegant explanation still needs rigorous testing before scientists accept it. And testing a theory this large required looking far beyond our own local neighborhood, out toward exploding stars scattered across billions of light years, searching for a consistent pattern that would either confirm or completely unravel the entire void-based explanation. Proving that a void could explain the Hubble tension required more than a clever idea. It required hard, testable evidence, and scientists found their best tool in a specific type of exploding star. These stellar explosions, called Type IR supernovae, share a remarkably consistent brightness no matter where in the universe they occur. That consistency makes them incredibly useful measuring tools. Astronomers call them standard candles because knowing their true brightness lets scientists calculate exactly how far away each explosion happened, based purely on how dim its light appears from Earth. A study by Chiang and colleagues, using standard candles, found supporting evidence for the KBC local inhomogeneity, adding independent confirmation to the original galaxy counting method used to first identify the void. Here is why this mattered so much. The original discovery relied on directly counting galaxies across different regions of sky, a method that could theoretically be thrown off by dust, distance errors, or incomplete survey coverage. Supernovae offered a completely different, independent way to test the same underlying claim using explosion brightness instead of galaxy counts. Think of it like verifying a rumor about your neighborhood using two completely different sources. First, you personally walk every street and count how many houses have lights on at night. Then, separately, you check the neighborhood's official water usage records, reasoning that empty houses use very little water. If both completely independent methods point toward the same conclusion, fewer occupied houses than expected, your confidence in that conclusion grows dramatically. That is essentially what happened when supernovae measurements lined up with the original galaxy counting results. Two independent methods, using completely different physics, both pointed toward the same underlying picture. An underdense region surrounding our galaxy, consistent with the KBC void's proposed size and shape. Researchers extended this supernovae testing further, checking whether the void's boundaries and depth, based on exploding star measurements, matched the predictions needed to actually explain the Hubble tension's specific numerical gap. This growing observational evidence for a large local void has increased interest in probing cosmological dynamics on a local scale, particularly measurements of the local expansion rate. The results were promising, but not universally conclusive. Some supernovae datasets aligned cleanly with the void explanation. Others produced messier, less definitive results, the kind of scientific grey area that demands more data before anyone can declare a final answer. This is normal, healthy scientific progress. Real discoveries rarely arrive as a single dramatic announcement. They accumulate slowly through independent confirmations, occasional contradictions, and careful, patient refinement over years of continued research. But not every scientist studying this question walked away convinced. In fact, some of the most serious pushback against the entire void explanation came from researchers modeling exactly how large a void the standard theory of the universe could physically allow. Their conclusions would turn this entire investigation into a genuine scientific controversy. Not every scientist studying the KBC void welcomed it as a tidy solution to the Hubble tension. Some researchers ran the numbers and reached an unsettling conclusion. A void this large should not be possible at all, according to the universe's own standard rulebook. It is debated whether the existence of the KBC void is consistent with the standard model of cosmology known as lambda CDM. While one research team argues that voids as large as the KBC void are inconsistent with this standard model, Another team argues that they are consistent with it. That direct scientific disagreement, two separate research teams reaching opposite conclusions using the same underlying physics, captures exactly why this remains such an actively contested topic. As for discovering whether supervoids like the local hole are possible within the standard model of cosmology, researcher Indranil Banik and his team found that such a large and deep void cannot arise in the standard model of cosmology, at least as it currently stands. This is a serious claim. It does not simply say the void is unusual or statistically rare. It says the void, if truly as large and as deep as measurements suggest, should not be able to form at all, given everything scientists currently understand about how gravity and matter behave across cosmic history. Here is a comparison that captures the weight of this disagreement. Imagine a team of structural engineers examining a massive bridge, one that has clearly been standing and functioning for years. One group of engineers runs every calculation using the standard building codes and concludes the bridge should have collapsed years ago, that its design should be physically impossible under normal construction rules. Another group, using slightly different assumptions, argues the bridge's design actually fits within acceptable limits after all. Meanwhile, the bridge just sits there, real, physical, and functioning, regardless of which group of engineers turns out to be right. That is roughly the situation cosmologists find themselves in with the KBC void. The observational evidence, galaxy counts and supernova measurements, keeps pointing toward a genuinely large underdense region surrounding our galaxy. But the theoretical models built from the standard picture of the universe struggle to explain how a void this size could have formed in the first place. This tension between observation and theory is not a sign that science has failed. It is exactly the kind of friction that drives science forward. When solid observations refuse to fit comfortably inside an established theory, scientists face a genuine choice. Either refine the theory to accommodate the new evidence, or find some overlooked flaw in the observations themselves. Both possibilities remain seriously on the table, and both carry enormous consequences depending on which direction the evidence eventually points. Because if the observations hold up, and the standard model genuinely cannot explain a void this size, the implications reach far beyond one unusual patch of the cosmos. They strike directly at the core assumptions underlying our entire understanding of how the universe is built. When observation and theory collide this directly, scientists eventually have to choose a side, or propose an entirely new path forward. For the KBC void, some researchers have started leaning toward a bold conclusion. Perhaps the standard model of cosmology itself needs revision. Our best theory of cosmology is wrong, researcher Indranil Banik stated plainly, adding that nature does not care about our theories, no matter how elegant or established they may seem. That statement carries real weight coming from someone who has spent years running the numbers, testing the void hypothesis against supernovae data, and modeling exactly how large an underdense region the standard cosmological framework should theoretically allow. The standard model in question is known as lambda CDM, a framework built on the idea that the universe consists mostly of a mysterious force called dark energy, combined with an equally mysterious substance called dark matter, both arranged according to a fairly uniform, predictable distribution across the largest cosmic scales. The presence of this local underdense region near the Milky Way attracts significant scientific attention due to its apparently huge size, precisely because that size challenges the assumption of uniformity baked into the standard model's foundation. Here is a comparison that captures what is at stake. Imagine a set of building codes that architects have trusted and relied upon for decades, codes that have successfully guided the construction of thousands of stable, functional buildings around the world. Then, one day, engineers discover a building that appears to violate those very codes, yet somehow still stands, still functions, still holds up under real-world conditions. That single anomaly does not necessarily prove the entire code system is broken, but it demands serious investigation, because either the anomaly reveals a flaw in the established rules, or it reveals some overlooked mistake in how that particular building was measured. Cosmologists studying the KBC void find themselves in exactly this position. The Standard Model has successfully explained an enormous range of cosmic observations for decades. But this one specific anomaly, a void potentially too large and too deep for that model to comfortably explain, refuses to simply disappear under continued scrutiny. Some scientists argue the solution requires modifying gravity itself at the largest cosmic scales, proposing alternative theories that behave slightly differently than standard gravity once distances stretch across hundreds of millions of light years. Others argue the solution lies in refining our understanding of dark energy, the mysterious force responsible for accelerating the universe's overall expansion. Neither explanation has achieved full scientific consensus. Both remain active, contested areas of ongoing research, tested against new data as better telescopes and more precise surveys continue coming online. What nobody seriously disputes anymore is the underlying observational pattern itself, a genuine underdensity surrounding our galaxy, confirmed through multiple independent methods. The disagreement lies entirely in how to explain it, and what that explanation ultimately means for the deeper laws governing our entire universe. Step back from the individual measurements for a moment and consider the bigger picture. If the KBC void truly exists at the scale scientists have proposed, the consequences extend far beyond simply resolving one stubborn number. The entire foundation of modern cosmology rests on an assumption called the cosmological principle, the idea that the universe looks roughly the same no matter where you observe it from, once you zoom out far enough. No special locations, no privileged neighborhoods, just a smooth, evenly distributed cosmos on the larger scales. A void as large as the KBC void directly challenges that foundational assumption. If our galaxy genuinely sits inside one of the largest known underdense regions in the observable universe, then our cosmic neighborhood is not average. It is unusual, potentially even rare, among all the possible locations a galaxy could occupy. Here is a comparison that captures the stakes. Imagine a research team studying global weather patterns by only gathering data from one small research station located unknowingly at the exact center of an unusually calm, low-pressure zone. Every measurement they collect looks consistent, internally logical, and scientifically sound. But if they mistake their unusual local conditions for the global average, every broader conclusion they draw about the planet's overall weather patterns risks being subtly, systematically wrong. That is the core danger scientists worry about with the KBC void. If we live inside an atypical region and mistake our local measurements for universal averages, some of our broadest conclusions about the universe's expansion, its composition, even its ultimate fate, could carry hidden, systematic errors. Resolving whether the KBC void is real and whether it genuinely explains the Hubble tension, therefore carries consequences reaching into nearly every corner of modern cosmology. It could mean revising how scientists calculate the age of the universe. It could mean adjusting predictions about how the cosmos will continue expanding over the coming billions of years. It could even mean reconsidering aspects of the Standard Model that have gone largely unquestioned for decades. This supervoid represents a genuine problem for cosmology, precisely because the Standard Model assumes matter should be more or less evenly distributed throughout the universe. Confirming a void this size would force that assumption to bend, if not break entirely. At the same time, resolving this question could also bring welcome relief. A confirmed local void explanation for the Hubble tension would mean physicists do not need to invent exotic new particles or entirely new forces to explain the disagreement. The existing framework of physics could remain largely intact, simply supplemented with the recognition that our own cosmic address happens to be unusually quiet. Either way, the stakes reach far beyond academic curiosity. They touch the fundamental story scientists tell about the size, shape, age, and future of everything that exists. And settling this question required one final step: comparing our proposed void directly against the most extreme example already confirmed elsewhere in the universe. Placing the KBC void side by side with the Bootes void reveals exactly where our cosmic neighborhood sits on the spectrum of possible cosmic emptiness, and the comparison offers real clues about which competing theory might ultimately hold up. The Bootes void remains the largest confirmed void discovered to date, spanning roughly 330 million light-years across, with a staggering 97% shortage of expected galaxies. The KBC void surrounding our own galaxy stretches even farther, roughly 2 billion light-years across, but with a comparatively milder 20 to 30% underdensity. Here is a comparison that captures this difference. Picture 2 abandoned buildings. One building, representing the Bootes void, is smaller overall, but almost completely gutted inside, stripped down to bare walls with barely any furniture left standing. The second building, representing the KBC void, is far larger in total floor space, but still holds a meaningful portion of its original furniture scattered throughout, simply spread more thinly than a fully occupied building would be. Both buildings qualify as unusually empty, but they represent different kinds of emptiness, one defined by extreme depletion in a smaller space, the other defined by enormous scale paired with comparatively modest depletion. This distinction matters scientifically because it changes how difficult each void is to explain using the standard model. The Bootes void, despite its severe emptiness, occupies a modest enough total volume that some researchers argue it remains statistically possible, an extreme but permissible outlier within standard cosmological simulations. The KBC void poses a tougher challenge precisely because of its sheer size. A void this large and this deep, according to researcher Indranil Banik's modeling, cannot arise within the standard model of cosmology as it currently stands, even though its internal underdensity is comparatively less extreme than the Bootes void's near total emptiness. In other words, size matters just as much as depth when testing these voids against theoretical limits. A smaller, more severely empty region might squeeze past the standard model's predictions. A larger, more moderately empty region, stretching across 2 billion light-years, pushes those same predictions past their breaking point. This comparison strengthens the case that the KBC void represents something genuinely unusual, not simply another example of the ordinary emptiness scattered throughout the cosmic web. Its combination of extreme size and confirmed location, directly surrounding our own galaxy, sets it apart from every other known void, including the far emptier but comparatively smaller Bootes void. Testing this comparison rigorously required more than telescopes and calculators alone. It required rebuilding the early universe from scratch, inside a computer, running the entire 8 billion year story of cosmic structure formation to see whether a void like ours could naturally emerge. Real telescopes can only observe the universe as it exists today, a single frozen snapshot after billions of years of development. To truly test whether a void like the KBC void could form naturally, scientists needed a different tool entirely. They needed to rebuild the universe from scratch, inside a computer. These reconstructions are called cosmological simulations, and they work by starting with a mathematical model of the early universe, complete with those same tiny density ripples left over from cosmic inflation, then running the physics forward across billions of simulated years, watching gravity slowly sculpt matter into galaxies, filaments, walls, and voids. Researchers assess the accuracy of specialized simulation codes in modeling the statistical properties of cosmic voids, validating their approach by comparing resulting void statistics against those obtained from full physics-based simulations. Here is a comparison that captures what these simulations attempt to do. Imagine an engineer wanting to test whether a new bridge design can survive a major earthquake, without waiting around for an actual earthquake to test it in real life. Instead, the engineer builds a detailed computer model, feeding in every relevant physical property, then runs a simulated earthquake, checking whether the virtual bridge holds up under the exact same stresses a real earthquake would apply. cosmological simulations perform the same function for the universe's structure. Rather than waiting billions of years to see whether a void the size of the KBC void naturally forms, scientists run the entire process inside a computer, compressed down into hours or days of processing time, watching billions of simulated years of cosmic evolution play out. The current cosmological paradigm explains the cosmic web's origin as the product of the formation and evolution of primordial density perturbations, superposed on a homogeneous and isotropic background, and simulations built on this exact framework have become one of the most important tools for testing whether specific observed structures, like the KBC void, fit comfortably within expected outcomes. The results from these simulations have fueled much of the ongoing scientific debate. Some simulation runs, built strictly within the standard model's assumptions, struggle to naturally produce a void matching the KBC void's full combination of size and depth. Other simulation approaches, incorporating slightly modified assumptions about gravity or dark energy, manage to produce structures more closely matching what astronomers actually observe. This gap between different simulation results mirrors the broader scientific disagreement discussed earlier. It is not that scientists disagree about the raw observational data. They disagree about which underlying physical model, when properly simulated forward across billions of years, actually produces a universe matching what we see. Resolving this disagreement will likely require even more powerful simulations, incorporating higher resolution, larger simulated volumes, and increasingly precise physics. Fortunately, that next generation of tools is already arriving, paired with an entirely new wave of telescopes designed specifically to map the universe's structure with unprecedented precision. Settling the KBC void debate once and for all will not come from arguing over existing data. It will come from gathering dramatically better data, and an entirely new generation of telescopes has been built specifically for that purpose. Modern surveys such as DESI and Euclid continue to trace billions of galaxies, refining our understanding of void shapes, distribution, and their role in resolving persistent anomalies like the Hubble tension. These represent a massive leap beyond the original 1980s surveys that first stumbled onto strange gaps in the data, where those early efforts painstakingly recorded a few thousand galaxies over months of observing time. Modern instruments can catalogue millions of galaxies with far greater precision, reaching billions of light-years deeper into space. Here is a comparison that captures this technological leap. Imagine the difference between mapping a city using a single person walking every street with a hand-drawn notebook versus mapping that same city using a fleet of satellites capable of photographing every building simultaneously, cross-referencing the results in real time. Both approaches produce a map, but one takes decades and leaves room for human error. The other takes months and achieves a level of precision the original mapmaker could never have imagined. Mapping and studying these voids helps astronomers probe dark energy effects, gravitational dynamics, and galaxy formation biases tied to this ongoing cosmic mystery. These modern surveys are specifically designed to nail down the exact boundaries, depth, and shape of the KBC void, with far greater precision than any previous measurement achieved. They will also search for smaller structures nested inside the void, testing whether its interior truly matches the smooth, moderately underdense picture proposed by earlier studies, or whether hidden complexity remains to be discovered. Perhaps most importantly, these new surveys will gather enough independent supernovae and galaxy data to finally settle the core question driving this entire investigation. Does the void's measured size and depth genuinely match what would be needed to fully explain the Hubble tension? Or does a meaningful gap remain, pointing towards some additional, still undiscovered piece of physics? Because voids are less affected by complex, non-linear gravitational dynamics, they remain particularly well suited for these kinds of precise cosmological tests, making them one of the most valuable targets for this new generation of instruments. Scientists expect these surveys to deliver increasingly confident answers over the coming years, as more data accumulates and more of the sky gets mapped in ever finer detail. The strange gap, first noticed by a small team working with a modest telescope in the 1980s, is now being chased by some of the most sophisticated instruments ever built. And as that data continues arriving, one final, deeply personal question remains unanswered, waiting at the very center of this entire cosmic investigation. Every piece of evidence gathered across this investigation points toward the same unsettling possibility. Our galaxy may not sit in an average, typical patch of the universe. We may occupy one of the emptiest, most unusual neighborhoods in the entire observable cosmos. The Milky Way sits within a few 100 million light-years of the KBC void center, not merely somewhere inside its boundaries, but genuinely close to its heart. If this measurement holds up under continued scrutiny, it means our galaxy occupies a statistically rare position, the kind of location that, if you picked a random galaxy anywhere in the observable universe, you would be unlikely to land on. Here is a comparison that captures how unusual this would be. Picture reaching into a massive jar containing millions of marbles, the overwhelming majority colored a deep, crowded blue, representing the dense, galaxy-filled regions of the universe. Scattered among them sit a much smaller number of pale, nearly colorless marbles, representing the rare, underdense void regions. Reach in blindly, without looking, and pull out a single marble. The odds strongly favor pulling a blue one. If our galaxy's position inside the KBC void holds up, it means we happen to pull one of the pale, colorless marbles instead, a genuinely uncommon outcome given how the odds are stacked. This raises fascinating questions that extend beyond pure physics. Some researchers have started wondering whether living inside an underdense region carries any broader significance for how galaxies, stars, and potentially life itself develop over cosmic time. Void galaxies, as discussed earlier, tend to form stars more actively and develop with less violent disruption from crowded neighbors. Could an entire galaxy's long-term stability, its quiet, undisturbed multi-billion-year history, be connected to the relative emptiness surrounding it? That question remains firmly speculative, far ahead of any confirmed scientific consensus. But it captures why this discovery reaches beyond dry academic debate about density, percentages, and expansion rates. It touches something deeply personal about our own cosmic story. Recent observational efforts continue confirming the presence and vastness of this large void in the neighborhood of the Milky Way, reinforcing, survey after survey, that this is not a fluke destined to disappear under closer inspection. If our galaxy truly occupies a rare, atypical position, tucked inside one of the largest known underdensities in the observable universe, it reshapes something fundamental about how we should think about our own cosmic address. Not one galaxy among a uniform, evenly scattered crowd, possibly one of the rarer residents, occupying one of the quietest, most sparsely populated neighborhoods the universe has to offer. And that realization brings this entire investigation to its final, most important question. What does all of this actually mean for how we understand our place in the universe? Every thread of this investigation leads back to the same starting point, a strange gap noticed by a small team of astronomers decades ago, working with a modest telescope, staring at numbers that simply refused to make sense. That gap grew, survey after survey, decade after decade, into one of the most significant open questions in modern cosmology. A void potentially 2 billion light-years wide. A galaxy, our galaxy, possibly sitting near its very center. A stubborn disagreement over the universe's expansion rate that this same void might finally help explain. None of this story has reached a final, settled conclusion. The existence of the local hole remains disputed among scientists, still hypothetical and still controversial, exactly as genuine scientific frontiers should remain until enough evidence accumulates to settle the debate one way or another. But uncertainty is not the same as ignorance. Scientists have confirmed, through multiple independent methods, that our galaxy's immediate cosmic neighborhood shows real signs of being underdense compared to the universe's overall average. What remains contested is not whether something unusual surrounds us, but exactly how large that unusual region truly is, and what deeper physics might explain it. Here is the final comparison worth carrying forward. Imagine spending your entire life believing your hometown sat in the exact center of a bustling, typical country, only to discover, through careful investigation, that your hometown actually sits near the edge of a vast, sparsely populated frontier, stretching farther in every direction than anyone had previously realized. Your daily life would not change. Your house, your street, your neighbors would all remain exactly the same. But your understanding of your own location within the larger world would shift dramatically, revealing a truth that had been hiding in plain sight the entire time. That is essentially what modern cosmology may be revealing about our galaxy's true address in the universe. Not a random, unremarkable location among countless identical neighborhoods. Possibly a genuinely unusual position, closer to the emptiest known regions of the observable cosmos than almost anywhere else a galaxy could exist. Telescopes keep improving. Surveys keep expanding. Supercomputers keep running increasingly detailed simulations, testing whether this enormous void truly fits within our understanding of how the universe formed, or whether it demands entirely new physics to explain. Somewhere in the coming years, this question will likely move from genuine scientific uncertainty toward much stronger confirmation, one direction or the other. Either the standard model of cosmology will need meaningful revision, or new discoveries will reveal some overlooked explanation nobody has considered yet. Until that day arrives, one thing remains clear. Every star visible in the night sky, every planet, every person who has ever lived, occupies a corner of the universe that may be far emptier, far quieter, and far stranger than anyone imagined. Right up until a small team of astronomers, decades ago, noticed the sky was a little too quiet.